Hello there, welcome back to A Slice of Physics. We're now going to talk about the basics of ray tracing, which is a very useful technique to figure out how images are formed when we use lenses or mirrors even. We'll first talk about the difference between converging and diverging lenses. Then we'll introduce some basic terminologies and concepts for ray tracing. We will discuss what the principal rays are, which includes something called thin lens approximation. And then we will talk about image types, specifically the difference between real and virtual images. So to begin with, let's talk about the difference between a converging and diverging lens. So when you have a converging lens, it's got a convex shape like this. It bulges out at the center, and it's called a converging lens because when you have parallel rays of light that strike it, they converge to a point. And when you have a diverging lens, something like this, it's generally concave, then rays of light that are parallel striking that lens will diverge after they pass through the lens. So the important thing here is that parallel rays of light converge or diverge depending on the type of lens. The important word is that only parallel rays behave this way. We will see later, and probably in the next video, that a converging lens can also diverge rays of light when the incident rays are not parallel to each other. Okay, I'm going to use this to build on a couple more things. Oh, by the way, some of you are probably wondering what I'm doing here. I had this ray of light going straight. For example, this one here, when it passed from air to glass, it still kept going straight, and it magically turned at the center point of the lens. And then it, based on our recent conversation of refraction, glass back to air. You know that's not what happens in real life. In real life, rays of light bend when they go from one medium to another with different indices of refraction. So there will be a refraction at the entry into the glass, and there would be a second refraction when the ray of light exits from the glass. But what we do is we use something called the thin lens approximation. And this is an easier way of dealing with refraction. So instead of dealing with two refractions, we just pretend that when the lens is thin, we pretend that the lens exists only at its center point. And so all the refraction happens at that center point. The important thing is that this simplification doesn't cost us anything. Pretending that all the bending happens at the center of the lens is still consistent with the two bends that happen at the entry and exit surfaces. So the rays of light after the lens, using the simplification, are consistent with what happens in real life, so we are good. So as we go, let me introduce some terminology. This plane at which we take all the refraction happening is called the lens plane. And generally we have a center line through the center of the lens that's horizontal. That is called the optical axis. So let me capture that here. According to the thin lens approximation, all refraction happens at the lens plane, and that includes the effect of the two refractions in real life. The next thing is when you have rays of light that are parallel to the optical axis, when they pass through a converging lens, they all converge at a point, as we already said, and that point is called the focal point. Or sometimes it's just simply called the focus. And then in the case of a diverging lens, where the rays are diverging after they go through the lens, if you trace those rays backwards, like we did in the mirror example, they all appear to come from a single point. And that point is called the focal point or the focus. So let me go ahead and add that description here. Parallel rays of light converge at the focus or focal point, and when they diverge, they appear to come from the focus on the other side of the lens. And then lastly, there is a property of the lens that's called the focal length. So if I have the lens over here, and here's my lens plane, and here's my focal point, the distance from the lens plane to the focal point is called the focal length, and it's written as this lowercase f. So this lens will have a focal length and a focal point on both sides of it, because the rays of light could be coming from the left, hitting it and then converging on the right, or coming from the right, hitting it and converging on the left. So you could have a ray of light that goes like that. And so it'll have a focal point on both sides, and it'll have a focal length on both sides. And we will be dealing with symmetric lenses where the focal length on both sides are the same. It doesn't have to be that way in real life. You could have a bulgy end on one side and a very flattish end on the other side with different focal lengths, but we will be dealing with symmetric lenses where the focal lengths on both sides are the same. All right, next let's talk about principal rays that we use in ray tracing. So I'm going to stick to converging lens for this discussion. So let me take a converging lens right here at the center. There is an optical axis that runs horizontally like this. There is a lens plane that runs right through the center of the lens and is perpendicular to the optical axis. And let me mark the focal points of this lens on both sides. Okay, so label these things here. And I'm going to take an object that's sitting on the optical axis. So let's just take this kind of an object sitting here. All right, so we're going to talk about three principal rays that really help us with ray tracing. So if I take rays of light from the tip of this object, you know that there's rays of light going in all directions from every point on this object. Remember, we said there is no shortage of rays of light. We can have as many as we want going in every direction in a straight line. But one of those special rays of light is going to be exactly parallel to the optical axis. So I'm going to number this. There are going to be three principal rays. So this is the first one, which is parallel to the optical axis. And the rule is that when it hits the lens plane, it's going to bend in such a way that it goes through the far focal point. No surprise there. We actually defined the focal point as the point where a ray of light that's parallel to the optical axis will converge. So that's our first principal ray. The second one is that there's going to be a ray of light from the tip of the object, let's say, that goes through the near focal point. Sorry, apologies for my hand drawing. These are supposed to be straight lines. Hopefully you can see them as such. So this second ray passes through near focal point. And that ray of light, when it hits the lens plane, is going to bend and become parallel to the optical axis. And then the third principal ray is going to be one that goes through the very center of the lens. So there will be a ray of light that's emanating from the tip of the object, and it passes right through the center of the lens. And that ray of light, it's a straight line, guys, continues straight without bending. Passing through the center of the lens. This is where the lens plane and the optical axis meet. That's the center of the lens. And the ray of light that's passing through the center of the lens will continue straight without bending. All right, let's recap some of the key conclusions here. There are three principal rays. The first one is the one that is parallel to the optical axis to begin with. And when it passes through the lens, that bends and goes through the far focal point. Second, a ray of light that goes through the near focal point. That's the focal point on the same side of the lens as the object is. So this blue one will bend and become parallel to the optical axis. And the third principal ray is the one that goes through the very center of the lens where the lens plane and optical axis intersect, and that one continues straight without bending. And these three principal rays will be very useful in us figuring out where images lie for objects and what their orientation is, etc. So in this example, the image of the tip of this object is going to be right there. And if you repeat this exercise for all the different points on this object, you will see that the ultimate image is going to look like that. It's going to be upside down and it's going to be sitting at this point. So this helps me introduce the last two terms that we want to talk about. And as we do ray tracing, one is the object size. So this object size is generally denoted as h. The distance of the object from the lens plane is generally denoted as s. And then there's an image size that's generally written as h prime. And then the image distance from the lens plane is written as s prime. So we got object distance, object size, image size. The last thing I want to talk about in this video is real and virtual images. So here, the image that is formed has rays of light that are passing through where the image is. So that would be a real image. So a real image is one where light rays converge at the image position. And a virtual image is one where you have diverging rays of light that appear to be coming from where the image appears to be. If you remember, we did this mirror example where we had a point object which was bouncing off rays of light from the mirror. And when these rays of light are all diverging, they're never going to meet on the left-hand side. But if you extend them on the right-hand side, we saw that they all appear to be coming from a single point, and that point is where the image of this object appears to be. So this would be a virtual image because it's a point of convergence of extensions of diverging rays of light. So this is a real image for a converging lens. Now, converging lenses can also form virtual images. We'll see an example of that later. But here we have real rays of light that are passing through where the image is. So it's a real image. And then here we have rays of light that are diverging, that are never going to meet. But then they appear to be coming from a single point behind the mirror. And so that's where the image appears to be. But because there is no rays of light there, it's a virtual image. All right, in the next video, we'll take some examples of this, but let's wrap this one up here with these basic concepts of ray tracing. So first, we discussed the difference between converging and diverging lenses and why they are called as such. They are all based on parallel rays of light. Then we talked about where the focal points are, which is the points at which parallel rays converge. Then we looked at these three principal rays, and we noted that rays that are parallel to the optical axis bend and pass through the far focal point. Rays that pass through the near focal point bend and become parallel to the optical axis. And then rays that pass through the center of the lens continue straight without bending. Then we discussed these terminologies, what a focal length is, what the optical axis is, what the lens plane is, what the image and object sizes and distances are. And finally, we discussed real and virtual images. So that is the summary here for the two different types of images. Real images are intersection of converging rays at the image position. Virtual images are diverging rays of light that appear to come from the image position, but there is no real light there. Thank you.